So, thank you. My name is Brodie, and I've been studying post-Newtonian close limit matching. So you have 4 binary black hole collisions in the head-on collision regime. So you have an approximation of the outgoing gravitational radiation, gravitational waves, when the 2 black holes are far away from each other. Now, there's a problem where it's good when they're far away, but as they start getting closer together, this approximation breaks down. And we know this because it deviates from the exact solution found by numerical relativity. And what we do here is present a novel procedure using Brodie approximates to continue on this approximation into the regime where the 2 black holes are close together. So now, why do we care about this? So the Einstein's equations are extremely hard to solve analytically. There's only been a few solutions, and they require usually an extreme amount of symmetry. Now, there was no way to exactly solve these equations until about 2005 when Manuel Campanelli and some others at RIT and Caltech and other places developed a method using supercomputers to solve these equations exactly. But the problem is that they take a lot of time, and since they're on supercomputers, they cost a lot of money. So we are trying to bypass this by using analytic methods to continue on this approximation that is very good when they're far away. The 2 black holes are far away, but continue it on until they're close together. Now, we have to start with the basics of general relativity. Now, here is a very compact form of the Einstein's equations, which are 10 coupled nonlinear partial differential equations. And if we were to write them out, we'd probably be here all night. So now it talks about space-time and matter, and can be put succinctly with John Wheeler's quote, "Space-time tells matter how to move, and matter tells space-time how to curve." So they're connecting to each other, and if you're dealing with vacuum space, which we are here, we can set this side of the equation to 0. Now, black holes, the basics of them. So black holes are there's a couple of kinds of them, and it consists of a small amount of solutions to the Einstein's equations that can be found analytically. The 2 basic kinds are Schwarzschild and Kerr. Schwarzschild doesn't spin, and Kerr spins. I didn't know that before the summer started, that black holes can spin. And there's a couple properties that are interesting about them. There's the event horizon, and this is for a Schwarzschild black hole. And after you cross the event horizon, there's neither light nor anything else can escape. Now, because the space-time curves so much. Now, once you get to the center of the black hole, there's something called singularity, where all of our equations blow up. Now, this is not just a mathematical coordinate singularity, because there's been different coordinate systems that have been studied to verify that this is really a physical singularity. Now, gravitational waves. Gravitational waves are caused by massive objects moving through space-time, and they send out like ripples in the curvature of space-time, as you can see here. Now, to get this equation, which is kind of like the differential equation for waves on a string, except in 4 dimensions, and we could find this through manipulations of the Einstein's equations to yield this wave equation. Now, we'll see here shortly what a gravitational wave passing through Earth looks like. It's some top secret footage that you might not have seen before, and I'm going to cover that. So, yeah, you've totally woken up one morning and noticed that your room was stretching and expanding. No, in 2005, when the first gravitational waves were detected, it was found that your room would only stretch and expand by 1/1000th the length of a proton. So extremely a small amount. You don't have to worry about it. Now, post-Newtonian theory, it's an approximation of the Einstein's equations when the 2 black holes are far away. Now, you could think of this as your regular Newtonian gravity that does not consider curved space-time, and some minor terms added on to the end of it to account for this curved space-time. In a weak field, though. Once we get to strong fields, usually you need numerical relativity, and that's why we're trying to bypass that, because of the time and the cost. And also, you need to worry if these black holes are moving extremely fast towards each other. This approximation also breaks down. There's also close limit approximation, which comes from black hole perturbation theory, where when these 2 black holes are very close together, you can consider them as one perturbed black hole, Now, a perturbed black hole is just like, say, distortion of a sphere. It's just a deviation from the norm. And this approximation is very good when these two are close together, so we can consider it exact. Now, we use the method that we use to continue on this approximation, the post-Newtonian approximation, into the closed limit regime is the Brodie approximation, which you can recast a series, which is the post-Newtonian equations can also be thought of as for certain orders as a truncated Taylor series expansion. So you can have this here, and the big thing with this is to find the different coefficients, like the a's and the b's, and there's different orders that you can choose, but you're limited with the amount of the orders that you can choose. So say you have m and n, you can for an nth power expanded Taylor series, you can do m plus n plus 1. That is your constraint for figuring out these orders. And you can manipulate it any way you want. Say it's 3 over here. You could put like 2, 2, 3, 1, and so you can mess around with it that way to form it into the way you want it. Now, this also alleviates some of the singularities that cause these approximations to not work anymore once the two black holes start getting close to each other. Now, you can also get a singularity from the Brodie approximate. Say if this was 1 and these coefficients sum to -1, your equation will blow up. But then the good thing about choosing those different orders and having some of that freedom is that we can avoid that most times. And usually this Brodie approximate, so you have your post-Newtonian approximation, which is good, coming from the side of infinity towards 0. But what you don't, and so the Brodie approximate will continue on the series in a good manner, where it does not deviate from the exact solution too much. But you don't have any, if you don't have any information from the other side, you can't use it as well. So what we do here is we feed it boundary conditions. So we know the event horizon of the black hole, and that's when we feed it here, so that we can get it into a nice form that matches almost exactly the close limit approximation. Now we can see here, over on the other side is we have 3pn and 2pn, and they look kind of different because it's the post-Newtonian is an alternating series. And so these are just series that are truncated at different points. So 3pn is a better approximation than 2pn. You can use it as the two black holes get closer together. Now, here we have the exact close limit, and the interesting thing is that we have these truncated series, and we can continue on their accuracy all the way up into this regime where the two black holes are close together. Now, this is just the outgoing gravitational, the amount of outgoing gravitational waves, and this is the distance from that the black holes are close together. So far distance away and close. So now there's no expectation when we recast these series with the Brodie approximate that it's going to come out to this form. And through the boundary conditions, we can have it form into this nice solution that goes to exactly 0 at the event horizon. Now, I've tested this in Mathematica, and you can increase these orders and get it to match exactly. But sadly, with post-Newtonian theory, it becomes harder and harder once you get to past 3.5pn, a certain truncation of the series, because then you have to start taking into account effects such as tidal effects, and then you have these two black holes coming together and the gravitational waves start bouncing off each other, and it gets very complicated. So this is very nice to begin our analytic approach to this, to use this matching technique to continue on the accuracy of the series from out here all the way to here, which has not really been done before. Now, future work, we'll go back to this graph here, will consist of, instead of the head-on collision, it'll be the in-spiraling collision, which normally happens with black holes. They don't usually come on to a path of exact alignment. And that'll be really interesting. And what'll be used is not exactly the Brodie approximate, but a different kind of asymptotic approximate that's being developed by Nick Barlow and Steve Weinstein here. And what that will do is it'll allow us to take solutions that work right here when they're close together, the exact close limit, and when the two black holes are far away, and find right in the middle what's happening, which, if it works to a great deal of accuracy, may alleviate the stress on numerical relativity to run all these simulations. Now I'd like to thank, many thanks to Manuela Campanelli, Brennan Ofek, and Nate Barlow for their lots of support throughout this summer. Thank you.
All right, we have time for some questions. Josh.
So yeah, everything I know about today was actually said by my student earlier. With the today you showed, how many terms of numerator and denominator?
We used a 1-1 for the 2p1 and then 2-1.
All right. Did you try other
We did, and it didn't fit as well. It was less accurate.
All right.
Other questions? I have a clarification question for you. I'm not sure if you mentioned it. When you say post-Newtonian terms, what does that mean physically in terms of the order? Right, so the post-Newtonian series is an expansion about a small parameter.
Yes.
What does 1pn mean? What does 2pn mean? Because you said 2pn and 3pn, and what do those terms correspond to in terms of the order counting of the series?
So it's an expansion in a small term, 1/c², and so each pn in this case, each term in the series will be so 0pn will be the first term, the 0th order approximation, and then 1pn, 2pn, 3pn, and so on.
Yeah, good. Yeah. Thank you. Any other questions? I mean, I could just sit here and ask you tons of questions all day, but I won't do that. We're not going to do that. All right, if there are no more questions, let's thank Liam again.